Social networks and online marketplaces often have a trust and safety team. The trust and safety team helps protect the platform from scams, fraud, and malicious actors. To detect these bad actors at scale requires building a system that classifies every transaction on the platform as either safe or potentially malicious. Since every social platform has to build some sort of trust and safety system, Smyte decided to engineer trust and safety as a service. Josh Yudaken joins the show today to discuss how Smyte engineered its platform to provide machine learning models for any organization that wants to take advantage of Smyte for its trust and safety. The tools we discuss include Kubernetes, RocksDB, and Kafka. So this is a great episode for anyone interested in data engineering or fraud detection or how to use cloud services and open source tools in unique ways. This is really a cutting edge infrastructure episode, and I hope you enjoy it. So you've got a bacon delivery service, and you need to notify your customers when their bacon has arrived at their doorstep. Twilio helps you make sure your customers get the bacon while it's hot. Twilio's programmable API lets you build SMS or voice alerts easily in the programming language of your choice, all in under 5 minutes with only a few lines of code. Now your customers get a text or a call the instant their bacon is ready. If your customers want to see the bacon frying on a hot pan, Twilio has video APIs and SDKs for the platforms that you know and love. Learn more at go.twilio.com/podcast and get an additional $10 when you sign up and upgrade your account. That's go.twilio.com/podcast. You will only pay for what you use, and it costs less than a penny to send a text. Get started at go.twilio.com/podcast. Get your bacon delivery service cooking with Twilio's APIs for voice, SMS, and video. Josh Yudaken works on infrastructure at Smyte. Josh, welcome to Software Engineering Daily.
Cool, thanks, Jeff.
Your co-founder, Pete Hunt, came on the show to talk about trust and safety challenges for software platforms and how to solve those at a high level, at a product level. In this show, I want to talk more in terms of the architecture, how you build a software architecture that supports the requirements for a scalable trust and safety system with Antifraud and other kinds of policing elements. So can you start by just explaining how Smyte works from the point of view of a customer? I know this would be rehashing some of the stuff that Pete talked about last time, but for people who didn't hear that episode, what does a customer do from the user's point of view on Smyte? How do they feed their data into Smyte? What is their experience? And then we'll talk about what happens on Smyte's side.
Yeah, sure. Okay, so from around day one, the initial customer will hook up to our API endpoint usually, which is just a simple JSON push to our api.smyte.com server. They can push kind of any payload they want. Generally, they will send username, user ID, whatever information, IP address, headers, usually in whatever format they want to us. And then on our side, we hook it up to our internal kind of data layout and then send that through our data pipeline. We also offer them a front-end piece of JavaScript, which they can throw on their website that records directly to us. And we also have client libraries for iOS and Android.
And on the back end, once Smyte is sending you their data, once customers are sending Smyte their data, Smyte consists of 3 parts at a high level. There's a real-time classifier, there's a historical classifier, and there is a manual review queue. Why are these 3 components together a useful high-level system for preventing fraud?
Yeah, sure. So the main component is the real-time classifier. So as the data comes in, depending on what the client actually needs, they can listen for responses in line. So that is, they send us an action such as a sign-up, and before writing that information to their database, they check with Smyte to see whether we will accept or decline the sign-up based on a variety of rules they can set up. Besides that, there is the slower one, which we will process in the background over the next 5 to 30 seconds and then send them a webhook with the response, which might be allow, block, or any number of labels which we have labeled that's simple action. From that, they can use that to stop kind of real-time attacks. But once you get a much larger scale attack or something that you didn't manage to block, we offer kind of a later stage, investigate your data, view top users, view basically divide it by anything and kind of scan through looking for malicious activity.
So the real-time classifier acts on the data stream immediately. The historical classifier runs some more computationally intensive analysis in the background. Can you explain the two?
Yeah, I mean, we also call that real-time. I mean, that will be done within 5 to 30 seconds.
Oh, okay. All right. So what is the difference between the types of analysis that the real-time classifier is running versus the historical classifier?
So the real-time one, I mean, so usually we try to respond to the customer within kind of 500 milliseconds, would be even sometimes too slow. So that really restricts what we can do. So we extract kind of as much information, but we won't tend to do outbound HTTP calls on that. We'll look up a bunch of counters, rate limiters, all of that, and use any rules that kind of take those pieces of data. The slower one will then maybe go up, and if there's an email address, it will check that the domain name that was mentioned exists, that it's running a mail server, and then check 15,000 different little services that we run.
So I think that a good way to ease into the architectural discussion for how Smyte works is this blog post that you wrote about counting at Smyte.
Sure.
Why is counting fundamental to spam, fraud, fighting, all the things that you're trying to police at Smyte?
Yeah, so I mean, I come from a general kind of infrastructure background, and so I haven't specifically dealt with spam before. But when we were starting to build the system, we chatted to a lot of people from Facebook, from Google, that have worked with these systems. And the thing we heard time and time again is that our main cost is going to be keeping all these counters, which kind of makes sense because if you want to know how many times you've seen, let's say, a given IP address in the last hour, we have to maintain a count of pretty much every IP address, obviously leaving out the ones we've never seen. But for our very, very big customers, that can add up to huge amounts of different counters. And we need to find ways to do that as efficiently as possible. From those counters, obviously, we can start writing rules saying if we've seen this user from IP addresses in different countries, that's pretty suspicious, especially if we see them in America and then less than 2 hours later in Europe, because you can't even travel that fast.
Do you usually need exact counts, or can you just get like fuzzy counts?
Yeah, so we have a whole lot of different counts for different purposes. The blog post is about exact counts. So that is exactly how many times have we seen this IP address in the last hour, in the last day, week, month. The other kind of counters, we use something called a sliding hyperlog log. That gives us approximate set counts. So we can say how many different IP addresses have we seen this user on without having to store every single IP address. That's surprisingly accurate, and it also gives us how many times in the last hour, day, week, month. We don't use count min/sketch yet, but we will be. That gives us kind of the same as before, but approximate counts rather than exact, with much, much faster, much lower storage, all of that.
So as you've said, your solution to counting is evolving, and it's always been evolving. What was your earliest solution to counting?
The earliest, I mean, this was kind of like day zero of the company as we were getting everything up. But we kind of just threw all the data in Redis. So we wanted to find out how many times we had seen, let's say, an IP address in the last day. We would create our buckets in Redis, increment it when we see it, and then we keep the last 24-hour buckets, summing them every time we want to get the count out.
And over time, Redis began to creak. It did not work. And you decided to switch to RocksDB. Why did you make that switch?
Well, the switch was made for a variety of reasons. I mean, Redis is very fast, very efficient, but it's all in memory, so there's no way that's going to be as cheap as it could be. The actual selection of RocksDB was kind of just briefly browsing around. We know a bunch of Facebook people. We know RocksDB is a solid product. We tried it out, and it worked fantastically well. Some of the advantages we didn't actually realize we were getting from day one is kind of its key prefix compression. So if you're counting, as I mentioned, I'll keep with the IP example, but if you're counting IP addresses, a lot of IP addresses start with the same couple bytes, and RocksDB won't store those bytes over and over again, whereas Redis would.
Talk a bit more about RocksDB, because I have not done any shows on it. I have been hearing about it more and more, especially in regards to Facebook. I hear it's such a crucial component of Facebook's architecture. What differentiates RocksDB from other databases, and how does it work?
Sure. So I'm not an expert on RocksDB, so I'm pretty sure the details I'm giving you are correct. It's based on the Google LevelDB product. Essentially, it's divided into two parts. There's an in-memory table for kind of usually the last 15 minutes of data, which is also synced to disk with a write-ahead log, which ensures once a write is committed, it will stay around forever. That table is then compressed into, levels in the LevelDB term. I actually can't remember what Rocks calls them right now. And then it kind of forms a tree of older data slowly moving down the levels, which get larger as they get bigger. And so the memory slowly moves down each level as the layers get compressed together.
Got it. So it's like a multi-layer LRU cache kind of, and each different...
Yeah, it's got a lot of similarities to that.
Right, interesting. And so at the higher up in the layers, the less compressed it is. So it's faster to access, but it's bigger.
It's faster to access. The files are a bit smaller. But yeah, overall, it just allows a way of kind of compressing the data. It also, it's called compaction. Sorry, I was just missing that word. Each level, as they compact it, it provides a solution for when you want to delete. So for instance, our counters, for a counter that we're only storing for the first day, we don't automatically delete it, but during the compaction step, when it joins multiple of these layers, that's when we say we'll just leave this record out since the count is no longer useful for us.
Well, what's the difference between compaction and compression?
So compression is taking a piece of data and storing it in less space, ideally, than it used before. The compaction basically will take two layers which are somewhat overlapping and join them into a single layer file. The other very interesting thing about RocksDB is those layer files are unique and will never change over time. They're static. So when you're backing up, it's very easy to back up individual files and confirm that they've been backed up successfully, which creates future backups will be much faster.
As RocksDB has become a crucial component of your architecture, the other crucial components of your data infrastructure, at least that you write about in that blog post, are Kafka and Kubernetes. Can you talk more about the interaction between these three components, why they make up your core infrastructure, why it's so useful, maybe particularly for the domain-specific database counting infrastructure?
Yeah, sure. So Kubernetes is more a side component as compared to Kafka and RocksDB, which we have kind of tightly integrated. So Kafka is very, very useful because it's kind of a write-ahead log in itself. So in the counter example, we will pipe data updates to Kafka. Those will be sent directly to the database, which will then commit on its own schedule. But if at any point that database crashes or gets moved to another host and it loses a chunk of data, it is very, very simple for it to just catch that data up from Kafka. Kafka has stored offsets which are idempotent, and it will know where it last committed, go back to the Kafka database, and read from there. Once that's up and running, the side component, which I mentioned, Kubernetes, helps us ensure these databases are always up and running. So when a database crashes or a machine crashes, Kubernetes will detach the persistent disks. So these machines run on beyond Google Cloud at the moment. and they run on Google Cloud persistent disks, which allow us to move them from machine to machine. So the disk will automatically be removed. It will be attached to another machine. The pod or the database will come up on that new machine with the existing data. Now, keep in mind, this sometimes takes up to 10 to 15 minutes. So the data will be a bit lagged at that point, but then it will connect to Kafka and then re-download and reprocess the last 15 minutes of data.
Software Engineering Daily has 20,000 engineers listening Monday through Friday. If you are hiring, or if you have a product that you would like to get into the hands of engineers, send me an email, jeff@softwareengineeringdaily.com. This podcast is sustained by the advertisers, and if you would like to become one, or even if you're just curious and you want to learn more, send me an email, jeff@softwareengineeringdaily.com. Thanks for listening. To get that level of functionality, basically you get distributed buffering out of Kafka, you get tiered database architecture out of RocksDB, and you get like uptime management through Kubernetes. I mean, 5 years ago, it would be inconceivable that you would get all of those things out of 3 components.
Yeah, so I forgot to mention the one part of Kubernetes called the services, which is actually, it's also kind of unbelievable. And when I first saw it, I didn't trust it very much because it's kind of magic. But essentially, they give us one IP address which references, so we run 2 replicas of each database, and Kubernetes services give us one IP address which references both of the databases, or whichever one is up and running if one of them crashes. Also, very importantly, which we haven't implemented yet, but during that catch-up period, we want to make it so Kubernetes does not register that database is ready, so that if one database goes down for 15 minutes, we don't serve the stale data.
Wow. Okay. Yeah. So the services thing, that's interesting. You mentioned that. I'm doing a show soon on Mesos and Kubernetes and sort of like their differences and why it's not a conversation of Mesos versus Kubernetes, but more like why they are kind of contrasting. They solve different problems, like some overlap, but the big topic, the big differentiator for Kubernetes, I haven't done that show yet, so I have to ask the person I'm interviewing, but seems to be the services aspect of it, like the fact that services are baked into it, and maybe I think the idea is like Mesos is better for data infrastructure workloads. But Kubernetes is really has the right abstractions, kind of the minimal abstractions for conducting your services. Does that sound accurate to you? Or maybe you didn't even look at Mesos, I don't know.
Yeah, I'll be honest. In the early days, we committed to Kubernetes fairly without too much discussion around it. It seemed like the correct product. We don't actually use much of the whole Hadoop, Mesos, Java situation. Not for any particular reason, just the components we use didn't need them, and it's a big setup.
Yeah, well, and I think like Kubernetes, this is just from like my talking to people, but Kubernetes seems to have like the same kind of feel as like React, where you just have this huge amount of people that are really excited about it for one reason or another. And I don't know if that's like Google drumming up the noise artificially, but I don't think it is. I think it's like people are really legitimately excited about Kubernetes, and so for whatever reason, I'm still not 100% sure why it's so popular, why it's so awesome, despite doing a bunch of shows about it. But there is like the network effects, and like people are really excited about it, and they're contributing a lot to it.
Yeah, just from using it, I guess it kind of feels like magic. You mentioned what we're doing now wouldn't be possible 5 years ago. And I'm from a Facebook history, and just seeing the tools for automatic, the containerization, fixing things automatically, dealing with problems, that all would have been kind of a nightmare to try build myself, but it's all built into Kubernetes. I also said a bit earlier that I didn't expect it to work out of the box. And literally as we turned it on, we originally didn't use services. We had a solution that was a little bit clunky, but kind of worked. And as as time went on, that started failing, and we just kind of looked at Kubernetes services, and they solved all of the problems we needed.
And today, I think most people that are running Kubernetes are using Docker containers for the compute substrate that you're managing, but there is work being done to make CoreOS just as usable as the container technology, I think. Or are you following that area closely, like what the compute layer that you can use is?
We're not following it too closely. We have had quite a lot of issues with the Docker compute layer. So I'm very happy there are competitors and there are other people trying to solve the problems in different ways. As soon as it gets to a point where it's kind of stable enough for us to investigate, we'll definitely look into it. Docker's also finally gotten to a point, at least for us, where it's more stable. The kernel bugs we were hitting earlier on seem to have mostly been solved. And it's stable enough for us to be confident running our databases in it, which I guess is a pretty big deal.
How do you feel about Docker? Because I hear some people say that, Docker is like reckless and they are over aggressive with pushing out breaking changes. And I don't know if this is like a small, loud group of people or if this is actually the case. What's your sense of that?
I mean, I don't actually know about the internal development system. Haven't dug into that so much. I can say the last couple versions of Docker, or at least not the latest, but the 2 or 3 before that, were fairly buggy. The Kubernetes initially recommended using Docker 1.8 or 1.08, I'm not actually sure, which was about a year old at that time, just because every version after that had some other significant bug, which didn't really work well with Kubernetes. At the same time, it is a very, very new product. The whole containerization solutions thing is also fairly new. So I'm pretty happy they're moving fast. It is unfortunate that it comes with bugs, but I guess that's one of the realities.
Yeah, exactly. Let's talk more about the broader architecture. We have discussed this Kafka, Kubernetes, RocksDB interaction that forms the backbone of your counting databases. Can you give me the bigger picture of the architecture?
So the counting databases and RocksDB are one component, but basically everything runs on top of Kafka. So as one of these API requests comes in with one or more payloads of actions, that immediately gets routed to our Kafka raw actions topic, and we respond to the client with a 200 OK. If they wanted a classification, it gets sent off at the same time to our classifier servers, and we'll wait on that response before responding to them. But once it's logged into the raw actions topic, it starts on our kind of data processing pipeline. The raw actions topic will then get picked up by our action workers, which use... So it turns out to be fairly difficult to load balance Kafka topics if you have way more consumers than the number of partitions, and also if those consumers are very slow. So Kafka consumers, usually you have, 20 to 100 topics. You have maybe 15 to 20 consumers processing messages very, very quickly. Our problem is some of the messages may take up to a minute to process. And while you're processing those, you want to be able to commit other messages that are processed on the same topic, or maybe divide those between lots of different processes. So we kind of have a middle piece in there that grabs a couple hundred Kafka actions from the raw actions topic, then serves them out to our action workers. Those action workers do all the processing, make any necessary requests, usually to a whole lot of microservices that we have running on Kubernetes. And then most of the output from that processing gets written back to Kafka. So this output could be increments of different counters. It could be labels that we've applied to that action. One of the things we dump is just a massive blob of features that then goes into kind of our historical views and into BigQuery, just a whole lot of different steps.
Yeah, sounds like it. Can you talk about any subjective architectural decisions you made? You described a lot in that explanation just now. What are the things where you or what is an example of something where you made a decision, you're like not totally sure about the decision, it's like still panning out, and you're like noticing the trade-offs in the architecture?
Yeah, well, so I mean, I can talk about a bunch of decisions that we've taken back, I guess.
Oh, okay.
So early on, we used MySQL pretty heavily, which I guess made sense. We also used React as a database and as a search engine, which, I mean, basically we needed a good key value store, and the fact that they had a search engine built in made it almost perfect for one of our use cases. The thing we're slowly realizing, and chatting to the Facebook and Google guys has reiterated that point, is that moving data between databases is very, very expensive. So even though React kind of magically scales for you, you don't always want that. It's I mean, one of our huge costs is between zones of the same data center in Google Cloud. They charge for traffic between the zones. You need to be in multiple zones for reliability, but you really want to control when data moves between them in order to cut down on that cost. And so we've kind of migrated away from these magic auto-scaling databases into a system of sharding that we can kind of dynamically update. So especially with, I mean, I go back to the counters because kind of everything centers around that.
Yeah.
But especially with the counters, we have this way of saying, okay, we have 20 shards now, but maybe starting from tomorrow, write the data over 30 shards. And so any old counts will still stick to the original 20, but any IP addresses that we haven't seen before will be divided over the new 10 as well.
So why does that yield savings versus the magical React database model?
I mean, well, the easiest to explain saving is just in that interzone transfer. So we pay per gigabyte to send data over Google's network. In the same zone, it's free, but between two separate zones, it's not. And if you want a reliable React service, you can't keep it all in one zone because that's a single failure instance, I guess. So you want to run React in multiple zones, but then you're going to be paying every time it decides to move a segment over. Whereas this counter system, the data stays where it's put originally.
I see, I think. So are you saying that you don't need to replicate those shards between data centers?
Well, so we do replicate it. So the counter's written to Kafka, and then we have two different databases in two different zones, which then pick up the updates. But once that piece of data is written, we're never going to move it to another server. If the server it's on dies, we will create a new server with the same ID and regather all the data out of long-term storage. But in the standard running without any machines dying, we are not moving data around.
So are you saying you just write so you write the updates to your database replicas instead of having React take care of updating its interzone replicas? So
whenever we get an IP address, we convert that to one of our internal IDs, which is a 64-bit number. But the important part there is that 64-bit number includes a timestamp. So now when we see a new IP address that we've never seen before, we can know that we haven't seen it before, A, and B, we know exactly the timestamp where we see it first will always be the same. And then we can actually shard based on that timestamp. So I can say anything that comes after February 1st, 2017, write it to these 8 shards, versus everything before that, write it to these different shards. And so kind of dynamically, as our system's running, we can change our sharding schema, which means even though we're not moving data around, we can ensure that old shards never get full.
So that's a very interesting example of a complex distributed systems decision that you made basically because of cost. Do you have any other examples like that where you realized like the economics of something were off and you wanted to make an adjustment based on that?
Completely. It kind of feels like my job these days is kind of balancing cost, reliability, and speed. And obviously you can't take all three.
And simplicity.
Probably the most significant one is trying to move most of our processing into a single zone, which is definitely kind of it reduces reliability a little bit. We do have a fallback that if that entire zone goes down, it'll be very, very easy for us to spin up the same processing in another zone. But that does give us huge cost savings, especially on that, as I mentioned earlier, that interzone transfer cost.
When you're talking about processing, what does that look like? Are you using distributed data processing frameworks like Spark or Flink, or is it much simpler work that you're doing?
It's much, much simpler.
Okay.
That's, I guess, another kind of architecture decision that we decided not to use Spark or Flink. Early days, we did investigate it, and it turned out to be kind of just too much work to get up and running originally, and we just needed to get something out the door. But as we got our solution out the door, it kind of made more sense to just keep with what we're doing. Essentially, what it started out with is one giant monolithic Node.js app. So action comes in, it's got a ton of microservices, but they were all built into the same app. Mm-hmm. And now kind of as time has gone on, we've started pulling out a bunch of those into separate microservices. Mm-hmm. And we're also looking at splitting out the main processing part into a much faster C++ or Python server.
Wow. So JavaScript is beginning to seem too slow for you.
Well, there's a whole bunch. Besides the things people usually hate about JavaScript, especially with kind of spam fighting, just the fact that it stores its strings as UTF-16, which means every time we're speaking to a database, that's just one small conversion to UTF-8 and back. But that happens just over and over again throughout our code base, and that actually it adds up to cost really. And there's a list of different things like that JavaScript does. We'll probably always have Node.js as our core system, and I really do love it for its ease of use and the speed at which you can develop. But in order to save costs, we are going to have to move some of those components to C++. We are looking at Python also for the easier to write, but still faster in some regards.
Now, the words machine learning can mean a lot of things. Can you describe what machine learning means in the realm of Smyte and what that machine learning architecture looks like?
We're also beginning to reinvent that piece of our puzzle, essentially. But from day one, we were not a strictly machine learning company, which I guess a lot of spam companies are. Our system is primarily rule-based. We're starting to develop one of our own kind of rule languages for a variety of reasons, but most of the spam fighting that happens on Smyte happens with this language and written in simple rules. We do use machine learning to identify text and as kind of a reputation system, so we can get IP addresses that have low and high reputation. And we are starting to develop a machine learning pipeline with TensorFlow and Jupyter Notebooks to build models into the system. But so far, the models kind of result in additional features that you can then write rules on. So you can write a rule saying if this IP address looks like a bad IP address according to the machine learning models, and they're making a purchase for over $300, then flag it.
When I'm choosing the tools for my side projects, the first thing that I look for is ease of use. That's why I love MongoDB. It is the most popular non-relational database, and it is super easy to use. At the beginning of a project, I often don't know the shape of my objects, and Mongo makes it easy to evolve the database schema as I like over time. Over time, as my project gets popular, I'm going to need to scale, and thankfully, MongoDB has built-in horizontal scalability, but configuration and database maintenance aren't really what I want to spend my time on. Thankfully, Mongodb Atlas was released in 2016. MongoDB Atlas is the easiest way to get access to MongoDB without having to run the database yourself. You pay only for what you use, from small projects all the way up to large production deployments. To try MongoDB Atlas today, go to mongodb.com/sedaily and get a free $25 in credit. Use promo code GOATLAS25 to get that $25 in free credit. Atlas is the only hosted MongoDB service built by the engineers behind the database, the company MongoDB. With Atlas, you get end-to-end encryption, you get VPC peering, you get access to the latest releases, and for a limited time, you can go to mongodb.com/sedaily, enter promo code GOATLAS25, and get that $25 in credit and get started with MongoDB Atlas. Thanks to MongoDB for being a new sponsor of Software Engineering Daily, and thanks for being the database behind a lot of my favorite side projects in the past. We're really happy to have MongoDB as a new sponsor of Software Engineering Daily. Much of the appeal of Smyte, from my perspective, is the idea that it's this product for developers at a company to use. Like Meetup, for example, uses it, and as I understand at least, they have developers in the mix who are using it. So, in some sense, like they need a simplified, consistent API that they can interact with to define rules and understand how they are going to be having, how their trust and safety infrastructure is going to work. So how does that translate to design decisions on your side? Like, I guess maybe is that why you started with the more simple rule-based model, because you really wanted to simplify the communication between you and the clients?
So we are essentially trying to build a spam fighting platform, kind of modeled after the things we've seen and heard about at Facebook and Google, where when you get an attack, you want a human in the loop to say, okay, I can see that this attack has these features going on. Let me write a simple rule and just start blocking those actions. From my days at Instagram, you can kind of look in the code base and there's a lot of evidence of the early spam fighting that went on, saying things like, if an email address starts in QZ and ends in @hotmail.com, just like block the comments for that. And that's what a lot of kind of websites tend to do. When they're getting this attack, they just want to write a simple rule, but they don't have this kind of extracted system in which to put the rule. So it just lands up in their main code base. So we're trying to build this additional system where you can write these rules very easily. They can do whatever you want, but they are kept in a separate repository. So what we actually give to these customers is a Git repository of their rules. I mentioned briefly the language, but it's written in something that looks a lot like SQL. And as soon as they Git push that to our servers, within a couple seconds, we'll process those rules and start running them on their live actions.
I guess this kind of stuff, because Pete talked about this too, about how he was the first engineer to join Instagram from Facebook once Instagram was purchased by Facebook, and he described like looking through the Instagram code base and being like, what is all this if-then stuff? And it was all like,
I mean, everyone has it.
Yeah, that's so interesting, and I guess that's just the low-hanging fruit of spam prevention. If these companies, they have to write some kind of anti-fraud stuff into their system, or anti-spam stuff into their system, because the spam gets so bad, and it all starts off with the same precautions that are the low-hanging fruit spam prevention.
Yeah, so I mean, our biggest competitor is kind of internal teams.
Right.
I mean, every developer thinks they can do this themselves, and for the most part, they can. You can get a very, very basic system up and running quickly. But yeah, where Smyte starts to shine is once you realize the things you actually need. So one very simple example is experimental rules. So when you write something to kind of block a huge category of people, you first write it in experimental mode. You look in our system, you see what it's blocking, and then you hit the enable this rule button. And I don't have any stories of my own, but I've heard a ton of stories of, like, you can block an entire country very easily with a slightly miswritten rule.
Right. And so I guess being able to canary that type of rule is really important.
Yeah.
So Smyte processes data in terms of events. So these customers that you have they're defining their rules, They're also defining their events that they are sending you. Can you give me an idea of like the life cycle of an event as it's getting processed by your system?
Okay. I mean, it's pretty much the cycle I mentioned before. So if I take, for instance, a sign up on Meetup, the user will go to Meetup, click the sign up button. Meetup will then send us this kind of payload with a little bit of information about them, the IP address, anything that's really relevant for the anti-spam system.
Mm-hmm.
That'll run into our Kafka topic for raw actions. We'll process it. We might label it as kind of one of the many categories of attacks they get. We might not if it looks good. We will then write that stream to our multitude of Kafka topics, which includes the increments and the labels. If it got labeled as a bad sign up, that would then get written to one of our webhook topics in Kafka, and then another consumer consumes that and then sends Meetup the information about the bad sign up.
You mentioned that companies have different things that they're trying to prevent. They might have different models that they defined that correspond to different bad actors. Can you describe how that works? Like, does the sign up on Meetup, does that get passed through these different models that they have, or I guess do they just define which types of models they want an action type to pass through?
I mean, this is all kind of defined in our rule system. You have this main squirrel file, which includes, you say include this bunch of rules if action name is sign up. And inside that file, you can then say things like block this action if this and that, and apply a rule saying maybe Meetup has like dating spam. So apply a rule saying this is dating spam to that specific action.
Okay, you mentioned SQRL, which is the Smyte query and rule language. That's a core feature of the platform. Why did you build your own query language?
Yeah, I mean, that's one of those things that looks like a bad decision from the outside, and I'm still not convinced everyone's wrong. But essentially, we didn't start out building our own language. We started out with a JavaScript-based rule language, and it had a whole host of problems. One of the biggest ones is it became very hard to statically analyze. It had a bunch of security implications that we dealt with as best as we could, but it still very much complicates things. One of the hardest things with JavaScript is because it's single-threaded, a while true loop originally in the original version would have crashed our thread. So we had to start using V8 kind of has this idea of isolated JavaScript processes. But once we started switching to Squirrel and I started turning those off, our system got a lot faster. It was way more of a speed burden than I even originally realized. But the biggest point is really the static analysis, where now when you write a Squirrel rule saying, I want to block if the count of unique IP addresses by actor is greater than 10, we will only start counting that once you've written your rule. Whereas the previous system, we had a list of like 1,000 things we counted, and we would count all of them independently of whether you used them or not.
What does static analysis mean in this context?
You write your Squirrel rule, which for instance says if number of IP addresses used by this actor is greater than 5, then stop him from signing up. I mean, that's probably not a rule you would want in your website, but it's a potential rule. We will, as soon as you get pushed that rule to us, we will go and look at the code programmatically and say, okay, you're counting unique IP addresses per actor. We will then set up a counter that counts every unique IP address used by the actor. That'll go down to our sliding hyperlog log system, but we will only start counting that once you start using it. What that does mean is if you add a rule saying count the number of unique IP addresses for this actor over the last year, as you push it, we will only have a few minutes of data. But we do have other ways of setting up counters in advance if you need that.
Why is a SQL-like language such a good dialect for defining rules?
The primary reason we actually wanted to go with SQL is a lot of these people that will be writing the rules are kind of spam analysts, and they all kind of know SQL. It's a very easy to understand language. It's declarative, which is great because it reduces the complexity. A single rule is only defined in one place, and there are no kind of if statements that are confusing things, no loops. It's very safe to run. We can ensure that the program terminates, for one.
So users don't ever define rules that take too long to run.
So we do have a whole lot of timeouts because that gets pretty complicated in figuring out how long each kind of step of the process will take. But yeah, so if they do define rules that take too long to run, we can track that very easily and let them know. But also all the other rules that didn't take too long will complete. And every other rule will fire if it needs to.
When a user wants to customize their rule set that they've developed, they can push these custom rules to Smyte via Git, and then there's kind of a continuous deployment process. Can you explain how that works?
Yeah, it's actually more simple than you probably realize.
Okay.
So we actually have it on a single server now, but we're in the process. I'm in the process of moving it into Kubernetes. But essentially, it is an SSH server, which then has a authorization kind of hook. So when it's the same way GitHub works, that authorizes you there. So when you SSH, we check that you're allowed to modify this repo. If you are, then a pre-receive hook, which is another Git, just in the .git/hooks folder, will automatically look at your changes, make sure they correct, make sure they parse. We actually do a bunch of error checking. So if you try use features that don't exist, we'll throw an error, which you'll get in your git push statement, and the push will not go through. If the push successfully goes through, however, we have this, we call it customer data internally, but we will write the file contents to console, which is...
Sorry, did you say console or console, like the HashiCorp
console,
thing?
The HashiCorp product.
Okay, right.
And then we write it to their key value storage, which all the processing boxes are watching for updates. So the second the update goes through, those boxes pick it up and start using that update. As a side process, we also have a kind of compilation step. So for older customers, so this is used for live updates, but for older customer data, we compile it on our dev machines and then upload that with a deploy. And then that gets overridden by any of the live updates.
Smyte can respond both asynchronously and synchronously to client requests. Can you give an example of when a client would want to do each of these different response types?
So the asynchronous response is really for the stuff that isn't as urgent that you need to respond quickly to the customer. So ideally, everyone would always use synchronous. But the problem with synchronous is that you need to wait for Smyte's response before letting the user know what has happened. So a good example of when you want that is maybe a sign-up, where you don't want to actually allow anyone to sign up if they're attacking you. So in your sign-up code, before responding to the user, so the user clicks the sign-up button, it hits your server, you contact Smyte, ask Smyte if it's okay. If we say yes, you respond to the user with okay. Otherwise, you might want to send the user a captcha if you're worried that it's a bot. There are any number of steps you can do, but the main thing about the synchronous part is that the user is in the loop. So you're still in a position to ask the user to verify something, maybe two-factor authentication if you have that, maybe a captcha, any number of things. Whereas the asynchronous part is really just kind of longer, slower processing, making sure you catch comments or follows or whatever's bad eventually, even if you don't do it within the first couple seconds.
I see. Right. So the synchronous is when you want to just, the user goes to sign up, and then the user is forced to block, waiting for Smyte's response to see if you give them the okay. And then the async.
Yes, I guess a good example of the synchronous, because we also do Antifraud, And a good example of synchronous is when you're processing a credit card transaction.
Right.
You'll definitely want to check with us first before putting that through.
Right. Asynchronous, though, you optimize for user experience. The user gets to go ahead and post their inflammatory comment, and then once Smyte calls back with the response that, hey, according to the model that you sent a request to, this is a spammy comment, and then maybe the comment gets deleted on the user's side.
If there's a spammy comment up for 3 seconds, it's not usually that much of a problem.
Right, definitely. So this, what's interesting about Smyte is it's this product that, this would have been useful like 5 years ago. It would have been useful 10 years ago. Like, this is a product that's like, why hasn't anybody made this yet? Although the architecture you're describing sounds really advanced and complicated, even though you are using these abstractions that make it simpler than it would otherwise be. Do you feel like this is this something that like people have tried in the past and they just haven't really been able to build something that's this robust? Or, I mean, like, why now? Why hasn't this been built before?
Yeah, I've done a bunch of startups, and that's a very important question to me. And I don't know if I have the best answer for you. I guess one of the keys as to why we built it is coming from that Facebook history, where Facebook was in a position where they have this multitude of different products, and they're like, how do we protect 12 different things where each one has different requirements? And I don't know that there have been that many companies in the past that have had a similar problem with the same kind of engineering culture that Facebook and Google have, whereas they want to build this one system that can deal with everything. And so there are a lot of different solutions to the problem, but I guess just none have had that history of, here is how we build this for 15 different companies that want to manage it themselves, not just... The other big problem I see is a lot of the pure anti-spam companies which try to solve this problem with machine learning and regular expressions just by themselves. And there have been a huge number of those over the past 10 to 15 years.
Why'd you go with Google Cloud?
The honest answer to that is they were the first people to give us $100,000 in credit. Since then, and as part of Y Combinator, we've gotten credit from a number of different cloud providers. Google, essentially, our system is built to look a lot like the Google infrastructure. And so being on Google actually helps us a lot. Things like Kubernetes, things like BigQuery, just having easy access to those are great. In comparison with AWS, I can't actually give you a strong answer. I think if we had started on AWS, our architecture would look a little bit different, but I don't think it would be better or worse.
Did you and Pete have domain expertise with AWS?
Yeah, I'd never used Google Cloud before. So here's the other thing. Google Cloud is much, much newer, so they've had this kind of opportunity to redesign their APIs.
Right.
And using Google Cloud APIs is really just a pleasure. Like, AWS is pretty archaic compared.
Right. Yeah, it's like the last mover advantage stuff.
Yep.
Yeah, and I think, I keep seeing articles about how much cheaper Google Cloud is.
I haven't investigated that because I guess I don't need to.
Yeah, you have the embarrassment of riches.
That's a great perk.
Yeah, okay, interesting. So, all right, I guess last question. What are some of the fundamental problems that, after you've been working on Smyte for a while, the fundamental problems that you feel are just going to be thematic that make bad actors so difficult to stop on the internet?
The biggest thing is it's just kind of this cat and mouse game where we need to stop them. Well, so the way we stop them is by finding identifying features. So let's say some spammer was really an idiot and he used the email, like every email address he used started with the word spam. We'd find it pretty easy to block that, and most users, there would be some legit users that have like spammy at whatever. But essentially we could, for the most part, block out that user maybe by the email address prefix and the IP addresses or reputation or whatever. The problem is once we start blocking them, the second you start blocking them, they will try get through. And so they'll maybe try change their birthday. Maybe they've been setting their birthday as the 1st of January because they never bothered to change the drop-downs. But as they keep trying, eventually they're going to figure out what you're using to block them, and then they're going to change that. And depending on how sophisticated your spammer is, they can get past almost, I mean, you can make yourself look as legit as you want. We've had some interesting cases of kind of owned devices where it is actually a legit device on a legit IP address. Everything about it looks legit, but it's also running another process which the spammer is using.
Indeed, the everlasting cat and mouse game between spammers and anti-spammers continues.
Yep, that's not going to end.
Okay, Josh. Well, thank you for making the time to come on the show. Quite an interesting architecture you're working on, and I'll be following Smyte closely.
Thanks a lot.
Software Engineering Daily is having our first ever meetup in San Francisco, January 11th at Galvanize. If you live in the Bay Area and you listen to Software Engineering Daily, please come check it out. I would love to meet you. We're going to have some awesome speakers. We have Pete Hunt, who is one of the early members of the React.js team, who is now the CEO of Smyte. Hasib Qureshi, who has been one of the most popular guests on Software Engineering Daily. Preeti Kasireddy, who has written about her career transition from venture capital to software engineering via Coding Bootcamp. Each one of these speakers is going to give an awesome talk, and I hope you can make it January 11th at Galvanize in San Francisco. You can sign up on meetup.com. You can also find the link on the Software Engineering Daily website, softwareengineeringdaily.com. I really hope to see you there.